Hello, welcome to the Personal Tutor Virtual Classroom. This is Physics for Senior High School, and we are still on the series Kinematics. Earlier in our lesson, we did look at solving problems using the Newton's equations of motion. Today, this is lesson number 5, and the caption is Graphical Representation of Linear Motion. The learning outcome would be at the end of this lesson, students should be able to know the various classes of the graphs of motion and provide detailed explanation and definition of the various classes of motion. We'll then also look at the slope that goes with each class of the graphs of motion. And finally, we'll make an interpretation of the graphs of motion, and the special emphasis will be laid on the velocity time motion graphs. So that is the learning outcome. Before we begin with the lesson of the day, let's do a recap of what we know before, and that is the relevant previous knowledge. During lesson number 2, we agreed that speed was mathematically equal to distance traveled over time taken. We did also see that velocity was equal to displacement over time taken. Lastly, acceleration was also equal to change in velocity of a body over time taken. This will be needed in today's lesson. So let's start with the various classes of graphs of motion. There are 3 of them. The first class is called distance time motion graph. The second, displacement time motion graph. And the third, velocity time motion graph. So these are the 3 classes of graphs of motion. Let's take them one after the other, starting from the distance time motion graph. And before even we go into the technicalities, you could easily see it's a graph whose axes are distance and time. So technically we'll say that the distance time graph is a graph of motion of a body that is represented by distance on the vertical axis plotted against time on the horizontal axis. This wise, vertical axis means y-axis, or in physics you could say ordinate, whereas the horizontal axis mean s-axis or abscissa. So that is the distance time graph. You can easily picture them as on the Cartesian plane. On the xy plane, we have distance plotted on the y-axis as against time on the s-axis, and that is the distance time motion graph. Now, it is said that the slope of a distance time motion graph represent speed. Keep this. And it can easily be proven that yes, it's true. When you take the slope of a distance time graph, what is otherwise known as gradient, we say slope is change in y over change in s. And on this, The y-axis is represented by distance, whereas the s-axis is represented by time. So you can also say that slope is change in distance over change in time. But remember that distance over time is equal to speed. So in actual fact, when you look for the slope, when you calculate the slope of a distance time graph, you have just found speed. That is why it said the slope of a distance time graph represents speed. Thank you. Taking the next graph of motion, which is displacement time motion graph. It is also a graph of motion of a body that is represented by distance displacement on the vertical axis plotted against time on the horizontal axis. And the graph look like this. On the y-axis, you have displacement in meters plotted against time and seconds. And for this graph, the slope of a displacement time graph represent velocity. And that can also be explained that, yes, a graph whose y-axis is displacement and s-axis is time, when you find the gradient or the slope, that is change in y over change in s, the y-axis is represented by displacement and the s-axis by time. But remember that whenever displacement is divided by time, it is equal to velocity. That is why the slope of a displacement time graph represents velocity. Let's take the next class of the graphs of motion, and that is velocity time graph. Just as we have looked at the true, this graph is also a graph of motion of a body that is represented by velocity on the vertical axis plotted against time on the horizontal axis. And graphically, you have this graph whose y-axis is velocity and s-axis is time in seconds. It is also said that the slope of a velocity time motion graph represents acceleration. And that can also be proven that when you have a graph whose y-axis is velocity in meter per second and time in seconds, the slope or gradient is calculated as change in y over change in s. The y-axis is velocity, and the s-axis is time. But remember again that velocity over time is equal to acceleration. Therefore, the slope of a velocity time graph represents acceleration. So friends, I believe you will keep this and you have understood it perfectly as well. Let's do a quick review or a summary of what we just said. If you have a graph of motion, what are their slopes? First, distance time graph. I believe you said speed. What of displacement time graph? You are right if you said velocity. Last, the velocity time graph. Its slope is acceleration. So take note of this as well. Let's then do an interpretation of the various graphs of motion. Let's start from the distance time motion graph. Friends, when you have a graph of this nature, and after plotting and joining the various plots or points, you get this straight horizontal line. This graph has a name, and the name is zero or no speed. It is called speed because it is a plot of distance against time. You can also call it uniform or constant distance, meaning in this case, the distance is uniform. Now, let me just put in some values to explain what we mean. We will do a detailed explanation with the velocity time graph. But with the distance time graph, what it means is at a time of 0, this body is at 15 meters. The time progresses to 1 second and the distance is still 15. 2 seconds, 15 meters. 3 seconds, 15 meters. 4 seconds, 15 meters. So what this says is, in actual fact, there is no speed. That's why it said no speed. It's also called constant distance because as the time elapses, still the body remains at the same distance. So notice that this is called no speed. Secondly, a graph of distance against time whose plot is this way. Not like the first. It starts from maybe the origin or any part, then it climbs smoothly like this. This graph is called uniform speed or constant speed. It is so called because when you project values on them, as the time progresses, so does the distance. So at a time of 1 second, you have a distance of 5 meters. The time moved to 2 seconds, then the distance also 10 seconds. 3 seconds, 15 seconds. 4 seconds, 20 meters. Notice, as the time increases by 1, the distance increases by 5. It has a uniform time increment and a uniform distance increment. That's why it is called uniform speed or constant speed. And it is speed because we are talking about distance against time. The next graph is this. This is called non-uniform speed. So look at this plot. If values are given on it, at a time of 1 second, the distance is 5. 2 seconds, it is between 5 and 10. So you could say 7.5. 3 seconds, 10. 4 seconds, 15. Then even at 4 seconds, you could still get 20 or 25 and so on and so forth. This is non-uniform because the time intervals and the distance intervals do not correlate. They do not correspond and increase by same amount. That is why we say it is non-uniform speed. The next graph is a graph of this nature, the blue line. With this, it is called decreasing speed. And this is the reason. If we give them values, at a time of 0 second, the body is at 25 meters. As the time increases to 1, the distance increases to 20, 2, 15 meters, 3, 10 meters, 4, 5 meters. If you notice critically, as the time increases, the distance decreases. And at 5 seconds, the distance is 0. This is what we refer to as decreasing speed. So I trust you have noticed all these four graphs. Very, very important. Let's continue with another interpretation of the graphs of motion. This time, let's look at displacement time motion graph. With the displacement time motion graph, any graph whose plots form this horizontal line that has a y-axis to be displacement and s-axis to be time is called zero or no velocity. It is velocity because when you divide displacement by time, you get velocity. You can say it is no velocity or rather constant or uniform displacement. That is, the displacement does not change while the time is changing and increasing. If you give it values as we did for the first, at 1 second it has 15 meters displacement, 2 seconds 15, 3 and 4 seconds still 15. So there is no velocity here, but there is a constant displacement. If you pick the second one, this increases steadily. This graph will be called uniform or constant velocity because when given values, an increase in the time from 0 to 1 second increases the displacement from 0 to 5 seconds, 5 meters, 2 seconds, 10 meters, 3 seconds, 15 meters, 4 seconds, 20 meters. There is an equal number of increment on both sides. For as the time go with 1 second incremental jump, the displacement goes with 5 and it is throughout. That is why it is called uniform velocity. The third graph, it will be called non-uniform velocity, in that the velocity is not uniform throughout. The increment in the time and that of the distance do not correspond, and so it is non-uniform. And the last graph will be called decreasing velocity, in the sense that when the time increases from 0 to 1, the distance also decreases from 25 to 20. Then at 2 seconds, 15, 3 seconds, 10 meters, then 4 seconds, 5 meters, then 5 seconds, 0 meter. So there is a recorded decrease in the velocity. So we call that one also decreasing velocity. So I trust you have noticed these four as well. Another interpretation will be made for the velocity time motion graph, which also follows the same trend, that a graph with a horizontal plot like this on a velocity plotted against time is called no or zero acceleration. It is acceleration because it is a plot of velocity over time. Or you can also say that uniform or constant velocity. That is, even though the time increases, the velocity remains constant and the same throughout. That's why it has this second name. Take notice of that. The third graph is called uniform or constant acceleration, in the sense that as the time increases by 1, so does the velocity increase by 5. So at every point, it has a corresponding incremental jump. That is why it is called uniform acceleration. Then the third graph is non-uniform acceleration. And as done or explained earlier, the acceleration does not become uniform when calculated. We will do a little mathematical calculations to prove what we are saying. And the last graph is called a deceleration. You can also call it a retardation. And in fact, it is also a decreasing acceleration. And lastly, a negative acceleration. So these are all names for it. And this is the reason. As the time increases, there is a notable decrease in the velocity. That's why we call it a deceleration. Okay, so I trust you have understood this perfectly. And as I said, it is also called negative acceleration. Okay, let's lay emphasis on the velocity time motion graph and know why they are called those various names. Starting with this graph, which we called zero acceleration, no acceleration, or uniform velocity. Why is it zero acceleration? So let's prove it. With these values given to it, let's label here as point A, point B, point C, and point D. At each of these points, we'll look for the acceleration. And I trust you remember that acceleration is changing velocity over time. So mathematically, A is V minus U all on T, where V is the final velocity, U initial velocity, and T time taken. So let's start with the point A. All we need is the initial velocity, final velocity, then time to calculate for the acceleration at A. This is where A starts from. And so its initial velocity corresponds to 15 meters per second. Then it travels down to the point A. The body stops at A, and if you trace it back to the velocity line, it is still 15 meters per second. The time will be 1 second. And so the acceleration at A is the final velocity 15, initial 15 over the time 1. And friends, 15 minus 15 over 1 is 0 meters per second square. Okay, I believe you have punched that on your calculator. Let's look at the acceleration at point B as well. At point B, the body is moving from A to B. Its initial velocity is here. When traced back, it is also 15 meters per second. It travels down to B. When you retrace the velocity, it is still 15 meters per second for the final velocity. At the time in question here is 2 seconds. Okay. Or you could let the body travel from the original point 0, so still 15, down to B, you still get 2 seconds. Then the acceleration here will be 15 minus 15 over 2. And that also gives 0 meters per second square. Let's jump the C and go to point D. At point D, let's still take from the origin. The body starts from here and its initial velocity is 15 meters per second. Travel down all the way to D. When you retrace, the velocity is still 15 meters per second for the final velocity, but the time has changed to 4 seconds. When acceleration is calculated, it will be 15 minus 15 over 4, and that also gives 0 meters per second square. So now I believe you have seen why it is called zero acceleration, meaning when the acceleration is calculated at every instant, it is 0, meaning there is no acceleration. It is also called constant velocity in the sense that both the initial velocity and the final velocity are the same. And in this our case, at every point, you get it all to be 15 meters per second. So that is why it has such name. Now, the second graph here is called uniform acceleration. So for this as well, let's calculate the various accelerations at each point. Let's call this one point A, point B, point C, and point D. The acceleration A still remains at v minus u over t. Let's start from point A. The initial velocity for point A is 0 meter per second. Then the body travels along this line, gets to A, making the final velocity to be 5 meters per second within a time of 1 second. So t is 1 second. The acceleration at A then becomes v minus u, 5 minus 0 over 1. And the answer is 5 meters per second square. That is for point A. For point B, the initial velocity, body starts from the beginning as well, with 0 meter per second as the initial. Then it travels down to B and attains a final velocity of 10 meters per second. The time is 2 seconds. So the acceleration is equal to 10 minus 0 over 2. And that also yields 5 meters per second square. Lastly, point C also starts from the beginning 0. It has initial velocity of 0 meter per second. Travels down the line to C and attains a final velocity of 15 meters per second. And the time is 3 seconds. Therefore, the acceleration will be equal to 15 minus 0 over 3. And that is also equal to 5 meters per second square. So friends, if you noticed, at each point, the acceleration is the same. It has a constant acceleration. It is uniform throughout. You can do that of the D and realize that it's also 5. So that is why it is called uniform or constant acceleration, meaning the acceleration is the same at every point. Thank you. Let's go to the last graph, which is called deceleration, otherwise retardation or negative acceleration. With this as well, let's label them. Let's call this side point A, point B, then perhaps this as point C. The acceleration is as stated. For this, let's look for the acceleration for point A and point C. So at point A, let's take it that I start from the very beginning here, 25. So that is the initial velocity, 25 meters per second. Then it travels down to the point A. This is the point A. That marks the final velocity as 15 meters per second. Remember, we are traveling downwards, and the time there is 2 seconds. The acceleration then becomes v minus u. The v is 15 minus the u 25. All over the time 2. Now 15 minus 25 is a negative 10 over 2. So A is equal to negative 5 meters per second square. Should we pick point C as well? Starting from 25 coming downwards. The initial velocity is 25 meters per second. Then it travels down to point C, which is here. That is 5 meters per second. And the time there is 4 seconds. Now the acceleration becomes v minus u. That is 5 minus 25 over 4. The difference of 5 and 25 is negative 20 over 4. And that will be negative 5 meters per second square. So this shows that there is a retardation because the acceleration is negative. So a negative acceleration simply means a retardation or deceleration. Thank you very much for staying with Personal Tutor. See you in the next class, which promises to be intellectually sound. Till then, stay blessed.